and welcome back. I meant to grab there we go. Meant to grab this book. Anyways, so welcome back. So last time we talked about just very simple idea of Beer's law and attenuation functions and things like that, and it really set up the problem of like what we're going to be actually dealing with. So generally speaking, the data that we're going to be getting is going to be coming from a CT scanner, and it comes in the form of, say, a sinogram. And what a sinogram is a collection of radon transforms through some sort of, quote, attenuation function, which could be a person, a sarcophagus, a monkey, anything. And could be a carrot. I hear that fruit and produce actually get scanned a lot in CT scanners and MRIs because they need to calibrate or just test one of these machines. They have their lunch available, so they just like throw it in and do a scan. So that's more or less the sort of data you're going to be getting. It's all from a sinogram, and it's going to be a collection of radon transforms. That's what the sinogram is. Each point on the sinogram is a radon transform. So, but the question is, what is a radon transform? We talked about it kind of lightly last time, and we didn't really go into it much. And I'm using this word sinogram. I'm not even sure if I actually defined it in last lecture. So we're going to be talking about that here in this lecture too. I happen to have already recorded the lecture. It's usually backwards from what I do. I usually record these first and then the lecture. But when I sat down to actually put everything together, I realized I hadn't actually talked about it yet. So in this lecture, what we're going to be doing is we're going to be defining what is called the radon transform. Now, the radon transform is what happens when you take a function and you evaluate it along a line, and then you take an integral on all those values. And this line goes from negative infinity to infinity. Usually the functions are fast decaying or have compact support, so that you can do things like exchanging intervals and other things like that to exploit various properties with, say, continuous or differentiable functions. So what we're going to be talking about today is the radon transform and a lot of different properties of it. Things like rotations of radon transforms, scaling of radon transforms, shifting of radon transforms, and seeing what happens to the sinogram on the other side. What this is going to do is that when we put these properties in combination with things like the radon transform of a circle or the radon transform of a square or other things like this, it gives us a collection of equations that represent the sinogram of these particular objects. So we can sort of get a closed form solution for the sinogram of, say, an ellipse, of a circle, etc. So that when we later come into it, when we want to describe for later, when we want to start with some sort of phantom, we know exactly what the sinogram is going to look like because we have it analytically. So that's what the bulk of this is actually going to be aiming towards, is like building up a whole bunch of collection of examples that we can later go ahead and turn phantoms into sinograms, so that we can do our inversion methods on those sinograms to see how well we can come back and hit the exact phantoms. And so generally speaking, you could always just try to do a numerical integration sinogram from samples from the phantom, but then that'll give you sort of a sampling of your sinogram, and then you're going to do a sampling of the sinogram to go back. And in practice, this is what you get, but then it'd start to confuse where your approximation problems are going to come from. You wouldn't know if it was the sampling of the phantom itself, the sampled sinogram, or the sampling of the sinogram. And so you want to be able to eliminate as many of these variables as possible when you're first testing out an algorithm. So having an analytic form for what the sinogram would have to look like gives you this nice way of avoiding doing an approximation of the sinogram itself. And so then you know that the only approximation that's coming into play would be in your inversion method. And so when you're testing out a new inversion method, this will give you a whole lot of things to do. So one of the first projects in the class that I'm teaching, if you're on YouTube, then you're free to try this out yourself, is to go into MATLAB and part of the project will be to go into MATLAB and create a a whole bunch of functions that will represent sinograms of, say, an ellipse or a circle, maybe a square. I haven't really thought that far ahead yet. In any case, yeah, so that should be fun. All right, so I guess I should just go ahead and let go and let you go take a look. I learned a lot going through this. You always just read through until you're actually forced to sit down and to actually do all these computations, and so yeah, so it was good exercise, and I encourage you to go ahead and try to do it line by line as well. So don't forget that we're following this book at this point, and this chapter, and this is Timothy Feeman's The Mathematics of Medical Imaging. We're going to hop around to several different books here and there, but for the first few chapters is pretty good for our graduate course. And so a lot of what we're doing in here is we're talking about the Radon transform chapter, and yeah, so we'll go through that. All right, thanks for listening, and I'll see you on the other side.
Okay, so last time we talked roughly about Beer's law and attenuation coefficients and whatnot. We had that 3x3 grid that we used as sort of a prototype example of sort of CT scan things that we cared about. And at the very end, we introduced something that we called the Radon transform. Okay, so the Radon transform is a transformation on a function, and essentially it is this. So say given an f going from, say, R2 to R of a particular type. All right, so a particular type we'll discuss later, but basically just assume that everything works for now. So integration is convergent and etc. We say that the Radon transform, well, probably with capital R, the Radon transform of f is given as R of f of t comma theta is equal to the integral of L of t theta f ds, where S parameterizes the line like we saw in the last lecture. Okay, so what we're going to do here, so I guess just say definition, and so we're going to assume that f is, decays fast enough, or it is zero outside of a certain region, or assumptions like that, so that we can go ahead and talk about this. Generally speaking, by the way, t is bigger than or equal to 0, and theta is in, say, 0 to pi. Okay. So, okay. And I mean, theta could be larger. I guess theta could be anything, but you'll have sort of a, you'll just repeat the same values after a point. In any case, so later on we're going to add in, so later we will talk about the Schwartz space to properly define the Radon transform. But you can still use ordinary calculus sort of ideas here. The Schwartz space basically, is basically the functions that are going to go to 0 really, really fast. So, say the Gaussian and things like that. It's also known as the space of rapidly decreasing functions. Now, I mean, you can talk about the Radon transform without talking about the Schwartz space, but you just always have to make sure that f is integrable along every single line. or you could restrict the lines of definition for the radon transform for other functions that maybe work for some t and theta and some not, but that ends up getting confusing after a while. And so we would like to be over a space of functions, a vector space of functions that where we can talk about the radon transform without worrying about this sort of thing. And so rapidly decreasing functions or compactly supported functions are usually the ones we'll talk about. But today, what we're going to do, today we will talk about properties. Of the radon transform. We'll also talk about, we'll show examples of transforms, and we'll also talk about what we call phantoms and sinograms. Examples, sinograms, and phantoms. And so basically the idea is that this is going to give us sort of a working knowledge of how of the sort of answers we're going to get out of using the radon transform. So for instance, if these examples that we're going to be looking at are generally going to be characteristic functions, so say a small disk in the plane, or a square, or an ellipse, or something like that, and then basically what we're going to see is that when we have a little circle, it's going to give us a sinogram like this. Now this is sort of our ground truth. So we know what the function is, and but generally speaking, you won't know when you take a general sinogram of like a CT scan out of a person or something in a CT scanner, and so this is going to be a sinogram, and this is what the actual data, the way the data will look like. And generally speaking, we want to be able to go from here backwards. But today we're going to be mostly talking about going from here to here. That way we know that if we design an algorithm that goes from here to here, we have a whole bunch of examples to test the algorithm and see if it's actually giving us what it should be. And that's what I mean by ground truth. So it gives us some way of measuring what's going on. So this is going to be in our XY space, and this is going to be in our T theta space. Right? Okay. And phantoms, this is an idea that was developed by Shep and Logan, or Shep Logan. I'm not sure, are those two different people? Or is that one person? Hold on, let me see. Shep and Logan, yeah, so two different people. So Shep and Logan introduced this idea of just basically design phantoms that look roughly like what you would expect to be inside, a person, like organs, things like that. But all they really do is they just put a whole bunch of ellipses and circles, squares, and things like that, and then that allows you to test your algorithm without worrying about the noise coming in from the data or the scanner. So then you know that if you see an error, that error is purely coming from your algorithm itself. But we have to build up to there, and so first we're going to talk about the radon transform, some examples, and its properties. Okay, so let's go ahead and jump into it. Okay, so the first example, and so here we're following Feynman's book. Mathematics of Medical Imaging, and so he has a bunch of really good examples just start with, and yeah. So first of all, we're going to suppose that we have a circle. So consider a circle of radius very small, 0.05, centered at 0,1. At the point 0,1. So okay, so so x is 0 and we're up at 1 and 0.05, so like what was that, 1/20th, something like that. Yep. And yeah, and so we're going to assume, and we're going to let f be equal to 1 if the point xy is in the circle, and 0 if x and y is not in the circle. Okay, you know how to express that sort of thing. And so yeah, and so basically what we're going to do is we're going to take an arbitrary. So what we're going to try to do is we're going to try to so we want to find the Radon transform of f, right? And so so here what we're going to do is we're going to have a graph. This is going to be what we call a sinogram. And we're going to say that theta is running from, say, 0 to pi. So this is theta, right? And we'll figure out what t has to be later. Because t could go up to 0 to infinity, but after 0 to pi, theta doesn't have to do anything else. So, okay, so, all right. So what we're going to do is we're just going to pick some arbitrary value of theta. Let's do this in a different color, pink, I guess. So we're going to pick a theta. And then the question is, we want to know when we're going to intersect the center of that circle. Okay, and so we want to figure out what this t value is here. Okay, well, if this is theta, and we want to figure this out, let's see. Okay, so it just takes a little bit of simple geometry. So let's give ourselves some space here. So we're saying this is theta. Then basically this is going to be 90 minus theta. Let's change the size of my pen. So this becomes 90 minus theta here. This is a right angle, so that makes this theta. So if we want to figure out what t is, this is our hypotenuse here, and this height here is just 1, because we said that this circle is centered at 0, 1. And so, yeah, so then if we want to figure out whatever t is going to be equal to sine of theta, right? So, thus, for any given theta, t equals sine of theta gives the line L sine of theta, which intersects the center of the circle. Okay, not too bad. So, what does that mean? Thus, oh no, now you got to suffer my handwriting this here. Let's zoom in again. So we'll say, thus, the Radon transform of f of sine of theta comma theta is equal to the integral of L sine of theta theta of f, we'll just say ds. And so basically this is a line that is going through a circle, and the is 0 out here, 0 out here, and 1 on the inside here. It's going straight through the center of that. And so we know that the radius of the circle is 0.05, and so it's going to be twice that radius, so it's going to be the diameter of the circle, 0.1. Okay, so now let's go back to our sinogram. So basically what we say, so we have this t here, and what we're saying is that if theta is equal to 0, then t should be sine of theta, so that should be 0. So so we'll just say that here, rather, since t is always bigger, t should start here. Okay. So, and we can keep following this along here, and let's see, so at pi over 2, sine of pi over 2 is 1, and we'll just say that this is at height 1, and so it's going to be up here, and at pi, sine of 0 is 0, right? So that's what we get. So, yeah, so now that's more or less what we're having. Now, as t varies between this band here and here, basically we're going to be having bigger and smaller contributions. So outside of a certain radius band of the of t, it's just going to be 0. And so basically it fades as it's leaving the center of this dashed line here. And so out here, this is all 0. Right? And so that's what we get. That's the sinogram for just this little circle. And so it's called a sinogram, mainly because it gives you things like this. Okay. Now, if I were to have a circle over here, see, at 1, 0, so here, then it'll give me, this will give cosine of it is equal to t. Okay, so that's the idea. And yeah, so that is our first little example. And so we see that if we have, say, a circle, then it's going to show up like a little like sine or cosine or something like that in our graph. Okay. Cool. So let's see. Now, let's go ahead and take a look at another example. And again, this is out of Feynman. So we're going to set so we're going to consider the region omega to be the closed circular disk at the origin. And with radius r bigger than 0. Okay. All right. The characteristic function for this, for omega, is given as we have the circle here, and the characteristic function is basically the function f of xy, which is going to be equal to 1 for x squared plus y squared is less than square root of r, and 0 for x squared plus y squared bigger than square root of r. And we need to put equal sign somewhere. We'll put it up here. Okay, so now let's see. So we're basically 0 out here and 1 on the inside here. Okay, so a characteristic function is basically a function that takes 1 on the inside of a set and 0 on the outside. So that's basically this. Okay, so now let's go ahead and start talking about the Radon transform. R of f of t theta. So some things we can say is that if, here, let's draw this again. So we have a circle of radius r here. And when we're talking about the Radon transform, we're given first a t value and an angle. And then we know that the line that we're talking about, L of t theta, is perpendicular to these two. So if we're outside of the radius r, so r of f of, say, t theta is equal to 0 if t is bigger than r, right? And r of f of, say, 0 theta is actually equal to 2r, right? Because you'd basically have a straight line right through the circle. Okay. How do we talk about other values? Well, let's see. So let's say we had, say, this t here, and we have some sort of theta here, and yeah. So let's talk about that. So we'll say this is t, and this is our right angle. We're going to be intersecting the circle here and here. Okay. So we don't really need to worry too much about all the little geometry in here. We just want to know what this length of the segment is. Okay, and since we're coming out from here, it's going to be sort of symmetric about this point. So okay, so giving ourselves another little circle to work with. It's not so cluttered. Basically, we have this, and it doesn't really matter the orientation because this is a circle and it's symmetric. So we have some t value that we're going up to here, and we're looking at sort of the intersection here and here. And we want to know what is the length of this, because basically that's going to give us our integral. Well, we can go ahead and describe this, this sort of graph as the square root of, let's see, square root of r squared minus t squared. So we're thinking of sort of the t-axis. And so here, when t is equal to 0, sort of lopsided, but whatever, we're going to be at r. And so that's going to get, and then twice of this is going to be 2r. And so then by the time we get up to here, this is going to be the square root of r squared minus t squared. So for t, t less than r, we have r f of t of theta is equal to twice the square root of r squared minus t squared. Okay, so that's good to write down. So basically now we get r of, let's change the thickness just to be consistent. So now we're getting r of t comma theta is equal to, is going to be 2 times the square root of r squared minus t squared for t, so value t less than square root of r, or less than r, and it's going to be 0 for So value t bigger than r. So I guess we're also assuming the convention that t could be negative, but having negative t really just means you flip the theta around. So whatever. Okay, cool. All right, so now we have two examples. We have one where we had a tiny little circle up here, and we got a sort of sinusoid. But now if we want to go ahead and graph this sinogram, then what do we get? Well, we know that, so going from 0 to t and 0 to pi for theta, basically what we're going to have is that by the time we get up to, say, r, we're going to be 0 past this, right? So 0 up here. And at 0, what do we get? Well, we could just get 2r. So basically, just trying to figure out a nice way of shading this. So basically what we do is, we get the height of, say, 2r up here, and it descends down to 0. Right? And so that is the sinogram for this. So we have two different circles, notice, and one we just found out the transform for the circle centered at the origin. What we're going to do shortly, although we are going to talk about a few more examples, so we're going to talk about a square and a cone next. But after that, our objective is to develop shifting properties and scaling properties. So basically we can shift circle anywhere we want, and we'll have a formula that'll give us what the radon transform is, and for any circle, and we can make the circles bigger and smaller. We still know what the radon transform is. We also would like to be able to scale in different axes, and if we do that, that'll give us ellipses. And so that gives us a whole bunch of different things that we can do in order to get sort of concrete examples or ground truths for various shapes. And so, since generally speaking we think of organs and other things inside the body as sort of blobby, we can sort of try to model them with a whole bunch of different circles and ellipses. Okay, so let's go on to the next example. So here we're moving away from the circle. We're going to let S be the square bounded by absolute value of x less than 1 and absolute value of y less than 1. So we are basically just talking about this. Right? So 1, -1. Well, I guess I should be a little bit more precise. It's going to be, say, -1, 1. It's going to be 1, 1. This is going to be, well, I guess we have all the points we need at this point. So 1, -1, and -1, -1. Right? Okay. So there you go. That's square. And we're going to let f be the characteristic function. So again, a characteristic function is a function that takes 1 inside the square. So f of xy is equal to, we're going to say 1 if the maximum of absolute value of x comma absolute value of y is less than 1, right? Less than or equal to 1, and 0 if, say 0 otherwise. So our function is 0 out here, and is 1 in here. Okay. So, so now we would like to talk about the sinogram of this guy, and that's going to be a little bit more finicky than just say a circle, which is symmetric with respect to theta. Okay, so we can talk about a few particular values of this. Otherwise, going through and like showing all the particular values would take a little bit too long and tedious to work out. Though keep in mind it would be, say, piecewise continuous or piecewise linear if we're going to describe it. But let's go ahead and talk about, say, theta value equal to 0. So we're going to take a look at r of f of t comma 0. And what do we get? So that's basically going to be where t goes along this line here, and so we're going to be taking a look at cross sections like this. Okay. Well, since the side length is 2, then basically we're going to get 2 for when t is absolute value of t is less than 1, and we're going to get 0 for the absolute value of t bigger than 1, right? Because once we exceed this area, that's it. Generally speaking, we also see that if we put in theta equals, say, pi over 2, we get exactly the same answer. If we have theta, t an absolute value is bigger than, say, square root of 2, then we know that rf of t theta is equal to 0 for all theta. If t is equal to, let's see, and then let's say that theta is equal to, say, pi over 4. What do we get? Well, in this case, we're going to be, say, the longest that we're going to have is it's going to be let's see, let's put in, we know that rf of, say, 0 comma pi over 4 is going to be equal to 2 to root 2, right? And if we take a look at t equals root 2, rf root 2 pi over 4 is just going to be 0, because it's just only going to cross that one point. And otherwise, it decreases linearly. So we see that rf of t at pi over 4 is equal to, it's going to be, let's see, 2 root 2 minus 2 t for absolute value of t less than square root of 2, and 0 for absolute value of t bigger than 2. So that gives you an idea of sort of what's going to happen. So in this case up here, we ended up having sort of a constant for t. This is constant of 2, and for here we ended up with sort of a peak here, and this was up at 2 root 2, and by root 2 we were done. So that sort of gives you an idea. The sinogram for this is a little bit harder to draw by hand, but just sort of going by what the book is. Let's see if it's impossible to do with this little pen and thing. We'll do a little MATLAB example later. But basically, the pictures for this look somewhat like this. Let's see. There you go. So that's 4 different little lines here that correspond to, say, the corners of our square. And so this is more or less what the sinogram is going to look like. Okay. So so here we have 0 and we have pi, and this is going to be sort of our t-axis. Okay, so that's more or less a discussion of what square would look like. Yeah. So let's go on to the next example. Okay, so this next one, we're actually going to be talking about something that isn't actually a characteristic function, but we're going to let f be given by, say, f of xy is equal to 1 minus the square root of x squared minus y squared for x squared plus y squared less than or equal to 1, and 0 for x squared plus y squared bigger than 1. All right, so basically what I'm saying is that we're going to be looking at the cone, right? And so this is height 1, and here is going to be 0, and this is the circle of radius 1 here at the base. Okay, so let's go ahead and we can actually exploit a couple of things about this line, these lines that we care about. So what we can say is that on the line, say L of t comma theta, we have that x squared plus y squared, the point on the line, which is parameterized by t cosine of theta minus s times sine of theta. So the parameter here is s. T sine of theta plus s cosine of theta squared. If you work all this out, you multiply it through and use the Pythagorean identity, what you ultimately end up getting is t squared plus s squared. So, basically, what we have is that f of t cosine of theta minus s times sine of theta, comma t times sine of theta plus s times cosine of theta is equal to 1 minus the square root of t squared plus s squared, and 0 for when t squared plus s squared is less than 1 or equal to 1, and otherwise for t squared plus s squared bigger than 1. Okay, so then if we want to ask what the Radon transform is, so we want to ask what the integral of over L of t comma theta is for f ds, then what is this going to be? Well, this is going to be the integral going from s is equal to minus 1 minus t squared up to the square root of 1 minus t squared of 1 minus the square root of t squared plus s squared times ds. And so this is, of course, provided that s isn't bigger than t squared, because if this is, of course, provided that t squared that isn't bigger than 1, or absolute value of t is not bigger than 1. So assuming absolute value of t is less than 1, then what do we get? After a little bit of trigonometric substitutions, ultimately this is going to end up giving you square root of 1 minus t squared minus 1/2 of t squared natural log of 1 plus the square root of 1 minus t squared divided by 1 minus the square root of 1 minus t squared. If anybody wants me to work this out, I'm happy to, but otherwise I'm just going to leave it here. So this is the Radon transform of f of t comma theta for the absolute value of t less than 1. And otherwise it is 0 for absolute value of t bigger than 1. Okay, so there you go. All right, so next we're going to go into properties of R, of the properties of radon transform. All right, and so so generally speaking, what do we get? First of all, the radon transform with a capital R is linear. That's easy to see. Integrals of t comma theta of, say, alpha f plus beta g. Well, integrals are linear, so it's f plus beta integral of g, L of t theta, L of t theta. And so this would be the radon transform of alpha f plus beta g. And this is equal to alpha times the radon transform of f plus beta times the radon transform of g. And of course, g here is going to go from r squared to r. And alpha and beta are in R, or you can even put them in C if you care. So there you go. So it is linear, and that really just follows from the linearity of the integral. And so all we have to assume is that g and f are both nice enough that the integrals exist on their own. Again, that'll come to considering certain classes of functions. So what we can do then is we can actually look at combinations of circles and other things like that in order to, like, say, chop out a chunk of a circle out of another circle and taking a look at our radon transforms. Okay, so what we could do is we can go ahead and take a look at a quick example. So we've been mostly talking about characteristic functions, and so we can split up this function f of x, y in terms of two characteristic functions. And so first let me give it to you. So we have one that takes value of 0.5 if x squared plus y squared is, say, less than or equal to 0.25. We can say that it's going to be 1.0 if 0.25 is less than x squared plus y squared less than or equal to 1.0, and 0 otherwise. So you can think of this in terms of having a difference of characteristic functions. So you can think of it as f being f of, say, region 1 minus 0.5 of f of region 2, where region 1 is equal to circle of radius 1 centered at the origin, and region 2 is equal to a circle of radius 0.5 centered at the origin. Okay, so we can immediately then use the other examples that we did, and so then we see that the radon transform of f of t theta is equal to the radon transform of f, the characteristic function corresponding to region 1 minus 0.5 times the radius, times the radon transform of region 2, and so that gives us this following bit: 2 times the square root of 1 minus t squared minus the square root of 0.25 minus t squared, if the absolute value of t is less than 0.5. and 2 square root of 1 minus t squared if 0.5 is less than absolute value of t is less than or equal to 1, and 0 otherwise. Right, and so and that's just using the linearity property and just comparing overlapping regions. Okay, cool. So next one's a little bit trickier, and that is what happens when we shift the Radon transform. All right. Okay, so now let's go ahead and talk about the shifting property of the Radon transform. So here we're basically going to be talking about a function. So we'll start with say given f r2 to r, just like we had before, and a g also from r2 to r, such that we have that g of x minus a comma y minus b is equal to f of xy. So we want to know what is the relationship between, say, the Radon transform of g, let's say t theta, and the Radon transform of f at t theta. Okay, so here's a general idea. So we have some sort of point here, say x comma y, and we're shifting it to this point, say x plus b, x plus a, y plus b. So this is what we're shifting everything to. Okay, so generally speaking, we are going to start off with, say, the Radon transform of f, and we're looking at it at, say, t theta and we're going to just fix theta. This is the line going from t comma theta of f, say, of x, y, say ds. So x and y are both parameterized by some s. And we also have dg of t theta is equal to the integral of lt theta, and here we're just going to put f of x minus a and y minus b ds. So again, x and y are parameterized by s. Okay, so something to remember is that for fixed theta, we have there exists a unique t and s in R such that we have x minus a and y minus a is equal to t cosine of theta minus s sine of theta, and we have y minus b is equal to t sine of theta plus s cosine of theta. Right. This is a linear transformation in terms of t and s, taking us to y of x minus a and y minus b, and it's invertible. So we can then extract, and this is straight out of the previous section, solutions here. So we have that t here, so this is going to be the shifted t, is equal to let's see, is x minus a times cosine of theta plus y minus b sine of theta, and then s shifted is something, but it actually doesn't matter. We're going to iterate over all of s, so we'll hit that point eventually. But the only thing that's really going to change is we're going to keep an eye on what happens to t. And if we take a look at this, we're going to have t shifted is equal to x cosine of theta plus y sine of theta, and then we have minus a cosine of theta minus b sine of theta. And this actually corresponds to the old t. So that means that, say, t shifted is equal to plus a cosine of theta plus b sine of theta is equal to t, or old t. So let's see. So what does that mean? So if we go ahead and take a look at Rg of t theta, and remember we're fixing theta, then this, remember, is the radon transform of the shifted. So say, so Rg of t theta is actually just going to be the same as Rf of t plus a cosine of theta plus b sine of theta, right? Comma theta. So we see that t is actually a function of theta, and yeah, that's fine. And this makes a lot of sense, right? So we saw before when we had a circle centered at the origin, the radon transform itself was just, it was concentrated here at the bottom of t, and then we saw that if we shifted up, then we ended up getting some sort of sinusoid. So we ended up having something like this, and so and that's when we shifted by b, and so we ended up having t being sine of theta, more or less, if we were following that particular point. And so, yeah, so that makes a lot of sense from some of the examples we've already seen. Okay, now scaling is a lot more straightforward. So scaling of the radon transform. Okay, so the scaling of the radon transform, what do we get? So what we're going to do is we're going to define this function. We're going to let h be a function from r squared r again, such that h of xy is equal to f of cx, comma cy with say y. Oh, sorry. Say c is in r, and I think it'd probably be best if we just say it's non-zero. Okay, so how are we going to do this? So really, I mean, there's not much of a change that ends up happening here. I'm trying to think of the best way to write this. Okay, so if we go ahead and take a look at, say, r of h at t comma theta, well, this might make the most sense if we just go ahead and take a look at L of t comma theta of h, and that we can write out as the integral from s equals minus infinity to positive infinity of f of t cosine of theta minus sine s times sine of theta times c. Let me just write this bigger. So we have t cosine of theta minus s sine of theta. I feel like s and sine are like the worst two things to have next to each other. And then we're going to have, say, t sine of theta plus s cosine of theta ds. This is an integral with respect to s. And inside of here, we're going to multiply these arguments by c. Okay, so the first thing we want to do is we can change s. We can set s prime is equal to, or let's say s twiddle. So we don't think this is a derivative, but s twiddle is equal to c times s. And so then that gives me ds twiddle is equal to c ds. Right, so first of all, that's going to go as 1 over c here times the integral of s is equal to minus infinity to infinity of f of ct cosine of theta minus s twiddle sine of theta, comma, ct sine of theta plus s twiddle cosine of theta ds twiddle. And this will be s twiddle goes from negative infinity to infinity. And so then this is actually going to be 1 over c times the Radon transform of f at ct comma theta. Right, so there you go. All right, so for shifting, it gives us this. So this is our shifted identity. And this is our scaled identity. Okay, so just briefly to mention phantoms. We'll go over this in the MATLAB segment in a little bit more detail. But basically, the idea of a phantom is that we're going to try to model, you know, what we'd see in, like, say, the brain or something like that. So there's something called the Shep-Logan phantom, and let me just pull up pictures so I can doodle it real quick, just to give you a brief idea. So the Shep-Logan phantom looks something like this. Yeah, very, very sketchy idea. And basically the idea is that this gives us a sort of ground truth for you know, all of our problems. So this is sort of an artificial mathematical model of like what a brain might look like, or a brain slice might look like. And the idea is that you get that we can produce sinograms for this, so something like that. And so this gives us so this is a Shep Logan phantom, and this is what we're going to use as our ground truth for our algorithms. So generally speaking, you start with a sinogram, and then we're going to go from the sinogram back to what we assume should be in our xy domain. And so this is in t theta. And so once we go back to our xy domain, this is going to give us sort of an approximation of what the original thing was. And so ultimately, using the fact that we know what it actually was, this Shep-Logan thing, or ones that we designed ourselves, we can actually get a quantitative comparison of, say, different algorithms and how well they're all doing. So because you can't do this with like a regular human subject. I mean, there might be problems with the sensor. You don't know exactly what's inside the person without just cutting them up. And so, so this score gives you an idea. The big thing about this, though, is that most of these phantoms are going to need you're going to need to know what the Radon transform of an ellipse is. So let's say Radon transform. Right. And so that way you can produce an exact representation of the cytogram without actually doing any sort of crazy computations. Okay, so this is going to be sort of a high-level sort of thing. This is the approach that Feynman took, and honestly, like a lot of this is just going to be basic geometry and algebra, and so it's not too bad. But we're going to go ahead and start with we're going to have an ellipse. So we're going to suppose we have an ellipse, say epsilon naught with corresponding boundary given by, we're going to have, say, x squared plus alpha squared y squared is less than or equal to alpha squared, right? And, it's going to be the boundary, and less than or equal to that is going to be the interior. Okay, so the characteristic function of that region is given by f of epsilon naught at xy is equal to say 1 for x squared plus alpha squared y squared less than or equal to alpha squared, and 0 otherwise. Okay, so if we're going to go ahead and get the Radon transform following Feynman, we're going to go ahead and express the integral in terms of its parameterization. So x equal to t cosine of theta minus s sine of theta, and y being equal to t sine of theta plus s cosine of theta, and this is for s going from, say, s in the reals. Okay, so then if we go and plug that in, basically what we're going to have is we're going to have some sort of an ellipse, and we're going to have this line going through it, and what we want to know is when we're inside, right? And then we'll take the other entries, and then we'll just take the difference between the two roots, and that'll tell us what the value is, because otherwise it's just the integral is 1. So if we plug these values in, and trusting Feynman here, basically what we get is we have sine squared of theta plus alpha squared cosine squared of theta, b is equal to t times sine of 2 theta times alpha squared minus 1, and c would be t squared of cosine squared theta plus alpha squared sine squared theta, and this minus alpha squared. And so this leads to this quadratic equation where we find the intersections of the boundary and the line. So we're looking for this, and that's going to give me these 2 points. Okay. What we want to do is, this is going to give me, say, some s naught. It's going to give me s1, and so then we're going to take the difference between s naught minus s1, and that's going to give me, or s1 minus s naught, and that's going to give me the length, or the integral, because otherwise the integrand is just 1. So this ends up being the Radon transform of f at t comma theta. Right? Well, since this is a quadratic equation, you can just use a quadratic formula, and that is ultimately going to give you, say, r of f epsilon naught of t comma theta is going to be equal to 2 times alpha times the square root of sine squared theta plus alpha squared cosine of theta minus t squared, and all of this divided by sine squared of theta plus alpha squared cosine squared theta. Right, and so there you go. And this, of course, is when t squared is less than or equal to sine squared theta plus alpha squared cosine squared theta. That should have been squared up there. And 0 otherwise. Okay, so then you can combine this with the scaling formulas. And so for general ellipses of x squared minus a squared plus b squared, y squared over b squared is equal to 1. What we can do is we can multiply and divide by multiply by a squared and divide by b squared, and so we get x squared plus a squared over b squared is times y squared is equal to a squared, and divide by b squared, it's going to give us x squared, say x over b squared plus a squared over b squared, and then we have y over b squared is equal to a squared over b squared. So here we get our alpha is equal to a over b, and we are scaling x and y by the same factor. So then if we call this say epsilon 1, what we find is that we have f of epsilon 1 of xy is equal to f of epsilon naught of x over b y over b. And so we can use our scaling formula. I'll leave that to you to figure out. And then you can use the other properties like the rotation and other things like that, which might just be more instructive if you do this with your homework, just to get some practice. And you can come up with formulas for rotations of ellipses and whatnot, and it'll all be based on this sort of thing. So I think I'm just gonna leave it here, and obviously you can do shifts as well, and maybe this is a good point to stop the lecture. So thanks for hanging in there with me, and I'll catch you next time. Okay, thank you for sitting through that with me. So now we know a bunch about the Radon transform. We know how to compute the Radon transform of a circle, for instance, and then even an ellipse. Then if we want to move the ellipse elsewhere, we can do rotations and shifts and all that, and we know how each one of those things are going to manifest inside of the Radon transform. So this is a good
collection of results so that we can actually test out our methods in later when we actually get to them. But next, what we're going to start doing is we're going to talk about back projection, and we're going to talk about not only back projection, but we're going to talk about the Radon's theorem, his inversion theorem. And so both of these are going to give us ways of trying to get back at the original image from the sinogram. And the sort of data that we're going to end up got a bit ahead of myself there. Yeah, so it'll let you get at the original image from the sinogram itself. The back projection is a really simple, like average of an integral of all the lines passing through a certain point, and then those will be applied to give you back the original image. But it's still going to be blurry. It isn't actually a very good method to do. The much more standard way to go about that is to use a filtered back projection, among other things. But before we do any filtering, we would have to introduce Fourier methods. And so after we go through the next lecture, which is a doozy of a lecture, it's like 2 hours long. So it'll be chaptered, and go through that at your own pace. It'll be the only thing I give you for that week, or at least for a couple days. And so then what we're going to do then after that is we're going to start going into the Fourier transform and Schwartz space, and talk about dual spaces and etc. And that all corresponds to the theory of topological vector spaces, but topological vector spaces, we're not going to delve too deeply into that because it turns out Schwartz space is actually metrizable. So if you know what metric is, and I have a lecture on that in my numerical analysis class, that's really as much of the topology as we're actually going to need. It's just convergence through metrics. So anyway, that's enough blabbing, and yeah, okay, I'll catch you in the next lecture. Take care.